Welcome to new session of the differential equation. In this session, we will discuss about the second part of the Bernoulli's differential equation. In the last session, we discussed it is that a Bernoulli first order Bernoulli's differential equation is of the form y dash plus f of x into y is equal to r of x into y raised to n is called a Bernoulli's differential equation. Here we discussed it is that this f of x and r of x are the functions of x alone or constants, functions of x alone or constant functions, constant values, and the n may be any of the real number. N may be any real number, any real number. And also we discussed it is that we can solve this to solve this equation number 1, we divide throughout with the y raised to n. So, we divide 1 with y raised to n, we divide 1 with the y raised to n. So, we will get the second equation. The second equation it is that y dash y raised to minus n into y dash. We divide y raised to n throughout with equation number 1. So, 1 by y raised to n into y dash is there. So, we will have the equation 1 becomes as y raised to minus n into y dash, y raised to minus n into y dash, and f of x into y raised to 1 minus n is there, f of x plus f of x into y raised to 1 minus n is there, and finally we will have r of x, it remains only there. So, this is equal to r of x. This is the equation number, this is the equation number 2. This is equation number 2. Okay, fine. So, then we will put a substitution as this is equal to, we put z equal to y raised to 1 minus n. Then we will have the differential equation can be changed into dz divided by dx is equal to 1 by 1 minus n into y raised to 1 minus n minus 1 is y raised to minus n into dy by dx is there. So, we will have 1 minus n into, we will have 1 minus n into just a minute, I did a mistake here, it is that 1 minus n into y raised to minus n into dy by dx is equal to dz by dx, and finally, we will have the, here it is that 1 by 1 minus n into dz divided by dx is equal to y raised to minus n into dy by dx. Okay. So, finally, our equation this one y raised to minus n into y dash is equal to 1 by 1 minus n into dz by dx, and f of x into z is equal to r of x. So, we will get the third equation 1 by 1 minus n into z dash dz by dx plus f of x into z is equal to r of x. This is our third equation. And finally, we will get the linear equation as z dash plus 1 minus n into f of x into z is equal to r of x into 1 minus n. This is the fourth equation. This fourth equation is the linear equation. This is an equivalent equation in z and x corresponding to our equation number 1, that is the Bernoulli's equation. We will solve this equation, linear equation, by the concept of the finding general solution of the linear differential equation. After getting the general solution in z and x, we replace z by y raised to 1 minus n, then we will get the actual answer of the general solution of the Bernoulli's equation. Now, this maybe always y raised to n need not exist here. Instead of y raised to n, there may have a chance to exist any of the functions in y other than y raised to n. See, we can move to a question. In that question we can discuss. Solve solve the Bernoulli's equation dy by dx plus x sin 2y plus x sin 2y is equal to x cube cos square y is equal to x cube cos square y. I just put it as equation number 1. See, dear students, while evaluating here we have f of x is here, this is our f of x, and also we have our r of x as x cube as r of x. We have x cube as r of x. See, my dear students, we have the term instead of y, here we will have sin 2y is there. Instead of y raised to n, we will have cos square y is here. Okay. While seeing, this is not like not a general form of the Bernoulli's equation. Even though this can be solved by using the concept of the Bernoulli's equation. In that Bernoulli's equation, we divide throughout that equation with the term containing y or the power of the y. Here in this equation, we divide, or this equation 1, we will divide equation 1 with a cos square y. So, we will have, while finding the solution, we can divide 1 can be divided with a cos square y. So, equation 1 becomes, therefore, equation 1 becomes as, say, 1 by cos square y into dy by dx, 1 by cos square y into dy by dx plus x into sin 2y divided by cos square y, sin 2y into cos square y. And finally, we will have x cube into cos square y divided by cos square y, the x cube only remains here. 1 by cos square y, the reciprocal of the cos square y is the sec square y. This implies sec square y into dy by dx is equal to the sin 2y, sin of y plus y. We can say that sin of y plus y is sin y cos y plus sin y cos y is there, 2 times of sin y cos y is there, plus 2 times of sin y cos y is there, divided by, in the denominator we have cos square y is there. Okay. Therefore, this is equal to, here we have cos square y is there. In RHS, the x cube only remains there. So, here this is equal to x cube. See, dear students, we have 1 cos y and 1 cos y we can cancel. Finally, we will have sec square y into dy by dx, sec square y into dy by dx plus 2 into sin y divided by cos y. Sin y divided by cos y, we can write that as tan y. And finally, we have here it is equal to x cube. This is the equation number 2. I would like to put this as equation number 2. See, my dear students, here we will have sec square y into dy by dx plus 2 tan y is equal to x cube. See, the second term it is there. Yes, here we have 1 x is there. I just forgot to give 1 x is here. So, this is the 2x tan y. Okay, fine. Okay, 2x tan y is there. Okay, fine. See, I would like to put tan y as z. Put tan y is equal to z. Put z is equal to tan y. Therefore, dz by dx, differentiate both sides, dz by dx is equal to derivative of tan y, tan y is sec square y, sec square y, as because this is a function in y, have to write a dy by dx with its, the dy by dx is there. See, sec square y dy by dx is the first term of the equation number 2, is the first term of the equation number 2. Therefore, this is the first term of the equation number 2. So, these are same. So, instead of that we can write dz by dx. See, 2x into z is equal to tan y. So, instead of the tan y we can replace with the z, and then finally, the RHS is x cube only is there. So, equation 2 becomes, put in 2, put in equation number 2, therefore, equation 2 becomes as, see, equation 2 becomes as, instead of sec square y into dy by dx, we have dz by dx is there, dz divided by dx, and then tan y, 2x into tan y, that is tan y is z, therefore, 2x z plus 2x z is equal to the r of x is there, that is the x cube. So, finally, we got it a linear differential equation. This is the third equation. Third equation is the linear differential equation in, this is linear differential equation in, this is a linear ordinary differential equation in x and z. Okay, fine. See, here we have f of x is there, f of x is the 2x is f of x, and x cube is r of x. This is our r of x. Fine. Okay. X cube is r of x. So, we can solve this by using the formula to find general solution of, to find general solution of 3, we use the formula z into integrating factor is equal to integral of r of x into integrating factor dx plus the constant of integration. We have to find the integrating factor. To find the integrating factor, to find integrating factor, sorry, to find integrating factor, if is equal to over some f of x, sometimes we will write the sum f of x, that is equal to e raised to integral f of x dx, e raised to integral f of x dx. Say, my dear students, if is equal to e raised to integral f of x dx, we know f of x is 2x. So, here we will have this is equal to e raised to integral 2x dx. Therefore, this is equal to e raised to 2 into x square by 2. Therefore, this is equal to e raised to x square is here. Can cancel this 2 and 2 we can cancel. Okay. Find the integrating, we found the integrating factor. Therefore, the if is e raised to x square. We have if is equal to e raised to x square. Fine. So, therefore, the general solution, see, fine. Therefore, the general solution is, we can put this as equation number 4, consider this as equation number 4, z into integrating factor. Therefore, general solution of 3 is z into integrating factor is e raised to x square is equal to integral of x cube is the r of x into e raised to x square dx plus constant of integration. Am I right? Yes. E raised to x square z into integrating factor e raised to x square is equal to r of x is x cube is there, and integrating factor is e raised to x square. Okay, fine. See, I would like to consider this as equation number 5. In 5, we consider I as integral of x cube e raised to x square dx. just if we evaluate that integral, we will get the solution. So, I take I is equal to integral of x cube e raised to x square dx, x cube e raised to x square dx, x cube e raised to x square dx. Okay, fine. Fine. Before evaluating this integral, I would like to just like to give this as, just I put 1 by 2 is here. For compensating that 1 by 2, I just put here 1 2 is here. Okay, fine. I would like to rewrite x cube as x into x square into e raised to x square dx. Fine. Okay. To solve this integral, I just put u is equal to x square, du is equal to 2x dx, du is equal to 2x dx. Fine. So, we can rewrite this as 1 by 2 is there in outside, 1 by 2 is there in outside, integral of this 2x dx. Actually, this x square is equal to u, this x square is equal to u, therefore, u into e raised to u. Fine. Therefore, we can write this as u e raised to u, u e raised to u, and 2x dx is here. This is the 2x is here, 2x is here and dx is here. So, 2x dx is du. Okay, 2x dx is du. Fine. Now, we just changed our equation I, the integral I into the term as u e raised to u du. Just evaluate that this is equal to 1 by 2 into integral of u e raised to u. We consider u as a first function and this u as first function and e raised to u as a second function. So, we will have this is equal to 1 by 2 into first function u into integral of the second function e raised to u minus integral of derivative of first function is derivative of u is 1, integral of second function e raised to u du. Okay. And finally, we will have this is equal to 1 by 2 into 1 by 2 into u e raised to u minus integral of e raised to u is again e raised to u. Okay. Now, we found u e raised to u minus e raised to u. Okay, e raised to u is common. So, we can take that is out 1 by 2 into e raised to u. So, we have here it is u minus 1. So, this is our I. Now, we can replace, see dear students, we can replace, we substituted u as x square. So, we can replace u by x square, replace u by x square. Therefore, I is equal to 1 by 2 e raised to x square into x square minus 1. Okay, that is I. That I we extracted from equation number 5. We can substitute value of I in equation number 5. So, finally, we will have therefore, general solution of equation 3 by substituting these values into equation number 5. The equation number 5 is actually z e raised to x square z e raised to x square is equal to then integral, that integral we found, and that is actually the value is 1 by 2 into e raised to x square into x square minus 1, 1 by 2 into e raised to x square into x square minus 1 plus the constant of integration is there. say I would like to take this e raised to x square to here and here. So, finally, we will have the value z equal to, we will have 1 by 2 into x square minus 1. There will be e raised to x square and e raised to x square can cancel, and plus c divided by e raised to x square is there. C divided by e raised to x square is there. So, that is z is equal to 1 by 2 into x square minus 1 into, sorry, x square minus 1 plus c e raised to minus x square. I just took that is into numerator, therefore, the power will be getting the opposite sign. Here the power minus x square is positive sign, in numerator that will have the negative sign. So, my dear students, this is the general solution of the equation number 3. Okay. Now, we can go back to our substitution for z. This is our equation. In this equation, we substituted for z as tan y. See, we substituted z as tan y. Replace z by tan y. So, finally, we replace z by tan y. Finally, we replace, finally we replace z by tan y. Replace z by tan y. Finally, we replace z by tan y. Okay. Finally, we replace z by tan y. So, we will have the equation will be z is equal to tan y, tan y is equal to 1 by 2 x square minus 1 plus c e raised to minus x square. 1 by 2 x square minus 1 plus c e raised to minus x square. This is the required general solution for, this is the required general solution for the, is the required for 1, that is the given differential equation that we did like a Bernoulli's equation. So, this is the method to solve either of the Bernoulli's equation, or sometimes some equation can solve by using the method of Bernoulli's equation, even though the RHS will not contain power of y, but maybe that there may contain a function in y, there may contain a function in y. Okay. There are many questions are available, interesting questions are available in the literature of the differential equation. Just write down some assignments related, just write down some assignments. First one, solve the differential equation y dash is equal to y tan x, y dash is equal to y tan x minus y square sec x, minus y square sec x, y tan x minus y square sec x. While rearranging this question, you can find the actual Bernoulli's, you will get the actual Bernoulli's equation. X y dash, next question, solve x y dash plus y is equal to x square y square log x, x square y square log x. You can add one more question as the third question as solve the initial value problem, solve the initial value problem, the IVP, y dash minus yx inverse, y dash minus yx inverse, sorry, y dash minus yx inverse is equal to 1 by 2 y inverse is equal to 1 by 2 y inverse where y of 1 is equal to 0, y of 1 is equal to 0, that is y is equal to 0 whenever x is equal to 1. See, dear students, you will get while solving the last question, you will get the general solution. In that general solution, finally you can apply y is equal to 0 whenever x is equal to 1. You are able to get the value, a particular value for c. Instead of general solution, you will get a particular curve that is passing through, that is a curve in a plane that is passing through the point 1 0. So, that will be a particular curve, that will be the particular solution for the initial value problem. Okay, you may try to solve these all questions. Thank you for watching this video. Continue your watching. Thank you very much.